Okay, so you have watched the basic concept of what a scatter diagram is in the last video, and also what you should really see is the videos that I have on interpreting linear equations, because interpreting the best fit line is the same thing as interpreting the linear equations. However, you may once in a while have a curve which is not a linear equation but some kind of a quadratic equation or a different kind. So in that case, it's different. But many of the problems that you see would be of like a straight line fit for the data. So let's look at a few problems. So here on the x-axis you have the swimming time, and on the y-axis you have the heart rate after the swim. So Michael swam 2000 yards on each of the 18 days, and you see those 18 points. The scatter plot above shows his swim time for the corresponding heart rate and after each swim. So the line of the best fit for the data is also shown. For the swim that took 34 minutes, Michael's actual heart rate was about how many heartbeats per minute less than the rate predicted by the line of the best fit. So what is it asking? It's asking if you compare the heart rate of Michael's heart rate by using the best fit line and the actual one, how much is essentially the difference between the two. So for the swim that took 34 minutes. So here we go look at x-axis 34, try to move up and see where the y-axis is. So if you see between 140 and 150, how is it broken down? So you see a horizontal line for every two heartbeats. Like if each one you can interpret as 142, 144, 146, 148, and 150. So that we can read these things correctly, I just want to point that out. So again, go to this x-axis 34, and on the best fit line it says that his heartbeat is should have been or is would be predicted as 150. But how much did we notice it is? It is 148. So the difference between the two is 2. So B would be the right answer. So this also illustrates the fact that the best fit line doesn't mean that it's the exact value. All it says is it is trying to estimate how much the heart rate would be at a given swimming time, but it doesn't mean that you would always get that exact value. So there is going to be an error. So this is, yeah, as you can clearly see, the points don't all fall on a line. So that's a concept you need to know. So you can never make a statement that says, yeah, it's always going to be on that straight line. So to highlight this concept, so in the previous example, we saw that the actual value was less than the estimate. Best fit line is good to interpolate or extrapolate. So interpolate means within the range of the data, somewhere some value you don't know, you're trying to guess. So, and also for extrapolation, but you need to be careful when you extrapolate. Extrapolate meaning going outside the range of the values that you already have. So if you're trying to, for example, in this case, extrapolation would be if you're trying to estimate how much would be the heart rate when the swimming time was 36.5 or 37 or even something beyond that. So you don't really have data to support it, but you kind of assume that it's in the same, it would be on the same straight line, but it is, you're more prone to be inaccurate when you go outside where the range of the data is. So for us, the data is within the range of between something between 34 and 36. So you're going to be more accurate if you try to predict the heart rate between those swimming times. So that's a notion that you should be aware of. Okay, here is another problem. So I don't know if you guys can read it. So if you can't, I'll just go ahead and read the problem. So the relative housing cost for a US city is defined to be average housing cost of this for the city divided by the national average housing cost expressed as a percentage. So that means if your city has houses that are 1.5 times the national average, so for your city the value would be 150% because it's 1.5 times more than the national average. So that would be your relative housing cost. And if your houses in your city are 20% lower, 80% would be the relative housing cost. So on y-axis you have the relative housing cost, and on the x-axis you have the size of the cities. So you might one thing that we notice is as the population of the city increases, so average housing cost also increases, relative housing cost, and the smaller cities they tend to be a little bit cheaper. So of course that's not the question that's being asked of us, but it is something that we can notice. So what is the question? The scatter plot above shows the relative housing costs and the population density for several large US cities in 2005. The line of best fit is also shown. So this is the line of best fit. So y is equal to 0.0125x plus 61. So which of the following best explains the number 61 in the equation relating to the scatter plot? So when x is equal to 0, that means when the population is 0, so y value would be 61%. Of course, in real life, you'll never have a city with a population of 0, but that means as you come closer to a very small number, so it would be about 61%. So that's what we know. So later, what are our choices? A. In 2005, the lowest housing cost in the United States was about $61 per month. So that's not the answer. The 61, we are talking about percentages. Here it says the housing cost is $61 per month. We don't know how much the housing cost is. So that's not the right one. So next choice is in 2005, the lowest housing cost in United States was about 61% of the highest housing cost. Again, what was the definition? The definition was that we are taking the average from the national average cost, not from the highest housing cost. So that's not the right answer. Third one, in 2005, even in cities with low population densities, housing costs were never below 61% of the national average. So this is the point that I was trying to make before. You cannot make absolute statements. You can't say it is never below 61%. You could have a housing cost even 41% for some house, but just means that in general as you come closer to low end you get to about 61%, but it's not an absolute. You can't make absolute statements of that nature. So C is incorrect. So the last one is in 2005, even in cities with low population densities, housing costs were likely at least 61% of the national average. It says likely. So that's in statistics, that's important to be able to say it is usually you're talking about you're saying in general this is the range within which it would be with certain probability or whatever, but you can't make absolute statements. So the answer D is the correct answer. So I'll see you in the next video.